Hello, everybody. This is chapter 9.1, looking at energy changes in reactions. First of all, we're going to go through the checklist, see what we need to know. You need to be able to describe the differences between exo and endothermic reactions. This is just in the difference between exothermic giving out heat to the surroundings and endothermic reactions taking in heat. You need to give at least 2 examples of endothermic reactions and 2 examples of exothermic reactions. The key thing here is that you need to be able to draw energy level diagrams for them. We'll look at the general energy level diagram for each of them, and you'll see that they follow a very particular pattern. You need to be able to state the unit used for measuring energy. In this case, we're going to measure energy in kilojoules. And we need to state what the plus and minus signs mean in energy values. What do they mean for whether a reaction is endo or exothermic? You can see that everything in this lesson is below a grade C. So if you're studying the core content, you need to know all of this. Okay, I've put a little link down here for the difference between temperature and heat. So if you're not sure on what that difference is, you can click on that link there and it will take you through this PowerPoint is on the Google Classroom. It'll take you through to one of my lovely little cheesy Eureka videos to look at the difference between temperature and heat, and I like the way that they explain it. So in the lab, when we come into the lab in the next couple of days, we're going to look at our own thermite reaction. This is called a thermite reaction. It's basically a basic displacement reaction where you've got iron 3 oxide. The aluminium is more reactive. So the aluminium is going to come in. We're going to give it a little bit of heat to start the reaction off. And then the aluminium is going to come to the iron oxide and it's going to kick the iron out and bond with the oxygen over here to make aluminium oxide, simply because the aluminium is more reactive than the iron, and the iron will be left by itself. But this sounds like a pretty dull reaction. I guarantee you it's not. They won't let us do this in the lab, so let me show you what a huge thermite reaction, 6 pounds of thermite, looks like. Here you go, 6 pounds of thermite. You see there's a little bit of energy going in there, and then wow, at minus 850 kilojoules for this reaction per mole of this reaction, you can see it's self-sustaining. Once you've got once you've put the little bit of energy in, the amount of energy that it gives out is pretty phenomenal. You can see that on the bottom down here, that's where the molten iron is, and it's so hot that the iron is completely liquid at this point. This is where there's another one. You can see that they are pretty exothermic, one of the most exothermic reactions that you will find. That there splashing down is the molten iron that's been displaced from the iron oxide. Okay, so obviously that's an exothermic reaction. It gives out heat to the environment. The most obvious of the exothermic and endothermic reactions, exothermic giving out heat would be something like a fire. Endothermic would be something that takes in heat from its surroundings, like melting a snowman, for example. How can we remember? Well, a good way to remember the difference between these two is that all the girls think exo are hot. So if you remember, like, exo are hot, exothermic reactions are also hot. I'm not sure if that's why they got their name, but exo are hot. Remember that. So let's have a look at some exothermic reactions in more detail. These 3 reactions here, acids versus alkalis, with any neutralization reaction gives out heat to its surroundings. It's an exothermic reaction. If you mix water with calcium oxide, sometimes called lime, common name lime, that would be an exothermic reaction. Exothermic reaction as well as respiration. That's why we are considered to be warm-blooded, why we can regulate our heat or warm ourselves up. We do this chemical reaction in our cells called respiration, and that actually gives out heat as a byproduct because it is an exothermic reaction. What do the energy level diagrams look like? Well, this might look a little bit complicated at the start, but it really isn't. If we look over here and we look at this is the amount of energy that is within the system. If we look that here would be the amount of energy in the products, in the reactants, sorry. So the reactants here have halfway up the energy scale. And that's the amount of energy that's locked in the chemical bonds. Now, what we would do is have to, let's say this is the thermite reaction. We put in some energy, we go up the slope here to the activation energy. The activation energy just means how much energy do you need to put in before that reaction begins. So you've got your reactants here just sitting doing nothing. We put a little bit of energy in up to the activation energy, and then the chemicals say, oh, okay, I want to start reacting. So when they start reacting, actually, they give energy out to the surroundings. Energy is actually released from the bonds that are locked up inside them. That energy can't be created nor destroyed. The energy that is released, once we go past the activation energy down here, we're back to where we started. We actually end up with the reactants here. The products have less energy in them than the reactants at the start. So if they've got less energy in, all this amount here has to have gone somewhere. It goes to the surroundings. So my surroundings would have gained energy. My surroundings would have heated up. So that's what all exothermic reactions look like in terms of an energy level diagram. A more simple way to describe this without the putting in the activation energy, this is how you will see it mostly. But we could do it a little bit more simply by looking at, here are the reactants, here's the amount of energy in the reactants, here's the amount of energy in the products. If the amount of energy in the products is lower, then energy must be released. So your reactants must have heated up. Okay? Let's have a look at endothermic. In endothermic reactions, all electrolysis is endothermic, and in other words, the surroundings will get colder if I mix sodium carbonate and ethanoic acid together, or the opposite of respiration, photosynthesis. Now that makes sense because if you look at the chemical reactions for photosynthesis and respiration, they are the exact opposite of one another. So if respiration gives energy to the surroundings, then reversing that reaction in a process of photosynthesis will be endothermic. It will make the surroundings colder. Now, these, for example, photosynthesis has very little, it's not like you stand near a plant and it feels cold. The energy change is very subtle, but that still doesn't mean that it's not endothermic. It's just very slightly endothermic. So let's have a look. You can see that the energy level diagram for an endothermic reaction is the complete opposite of that of an exothermic reaction. So if this is the reactant, again, we've got to put some energy in to get it all going. So we put some energy in, we go up here. This is you putting energy in to make the reaction happen. Putting energy in, usually in the form of heat, and then when the products are made, the products have more energy than that of the reactants. So therefore, that energy has to have come from somewhere. To get from here to here, to jump up from here to here, you must have got that energy from somewhere. The only place they can get that energy is by dragging it from their surroundings. So they absorb it from their surroundings. Have a look here at the more simple version. If your reactants here are of a lower energy than the products, then that energy must be absorbed from the surroundings. So your surroundings get colder. So that's really it for endo and exothermic reactions. Remember that exothermic reactions give energy to their surroundings, and endothermic reactions take in energy from their surroundings. We'll look in more detail in the next video about what that actually means in terms of the chemical bonds. But for now, that's it.